So here is a question. Prove that S squared is unbiased estimator of sigma squared. Now, what are we really talking about for this question? What I want to prove is that when you have got a sample, let's say you have got 1000 people, and of the 1000 people, say you want to see how much a certain condition is affecting them. But you might not manage to do an experiment or to carry out your survey with the entire population that you have. Instead of the population of 1000 people, you might just get, let's say, 10. So the 10 is going to be a sample. So we use Greek letters like sigma to represent a population, and then English letters like S to represent a sample. So what we are saying is that the estimator variance, because s squared is a variance, and the square root of s squared, that is s, that's the standard deviation. Want to prove that a estimate of the variance is going to be, this is for the sample, is actually equal to the population variance. In other words, when we just get a sample, it is the same as the actual population that we are dealing with. So that is what we want to prove. So to start with, what we're going to be dealing with is we're going to be dealing with this part, and we want to show that the estimation is equal to the actual population variance. So what is the first thing that we're going to do? So I'm going to write that the estimate, sorry for that, the estimate of the variance squared is equal to the estimate, or the sum of all the numbers from the first term to the last term, and then x minus mean squared. What I'll do is that I'll leave out the denominator first. I'm going to bring the denominator in later on. And this is going to be equal to the estimate. We are going to have a summation from the first term to the last term. I'm going to expand x minus mean squared. I'll get the first term, which is x. I'll square it. Okay. And then I'm going to get the power 2. I'll multiply with what is inside. That will be 2x times mean squared, no, just times mean, and then we'll get now the mean, we square it, so that is going to be positive. If you want, you can write these 2 times and then you start expanding. And then at this point, I'm going to distribute the summation symbol. So I'm going to have summation from the first term to the last term of x squared, and then I'm going to get the 2 and the mean, put them together. So that is going to be 2 and then mean. And then I'll distribute this summation. I'll put the summation here, and then I'll put x. Remember, it is from the first term to n. And then we are going to have also the summation from the first term to n of the square of the mean. Okay, so at this point, what else should we know? What we need to know is that when you have been given, how do you find mean? Mean is given by, you get all the numbers. If you have got 5 numbers, you are going to get those 5 numbers, you add them. So we are saying it is x, and then you divide by how many they are. Let's say you are talking about 5 numbers, so you divide by how many those numbers are, and that is basically n. So you add all the numbers and then you divide by how many they are. If I want to make this term the formula, the summation, so I'm going to have summation from the first term to n of x. That is going to be n, the denominator multiplied with the mean. So that is going to be it. And then from here now I'm going to get this term. So we have got estimator or estimated. We have got summation of x squared, and then we have got minus, okay, sorry for that, so minus 2 times the mean. But now where there was summation of x, can you see where the summation of x here? I'm going to substitute. Remember, summation of x is the same as n times mean. Okay, and then we have got plus we have got summation of the mean squared. But again, another thing we need to know, say if you have got x plus x plus x plus x, what are we going to get? There are 4x's. It will just be 4x, isn't it? This is telling you that when you have got a summation, okay, the summation of a number from the first term to the last term of that number, simply get that same number, x multiplied by how many there are. Like here we have got x, x, x. There are 4 of them, so it will just be 4x. So if you are adding numbers from the first term to n, just multiply how many those numbers are, so it will be n times x. So that is what we are going to do with the mean. Same if this was x squared plus x squared plus x squared plus x squared, it will be 4x squared. So here I've got a from the first term to the nth term for the mean squared. So that is going to give us what? That is going to simply give us n times the square of the mean. Okay, it's the same principle that we have used here. So if this was x squared, this would be x squared, but if it was a mean, it would still be the mean squared. I didn't do the same for this x, I've just left it out because there's another principle that we're going to use. So that is going to give us mean, and then we have got the summation from the first term to n of x squared minus 2x mean and n. So if you multiply this, what are you going to get? The mean and the mean will multiply, so this will give us negative 2n with the mean squared. So the negative 2n with the mean squared plus n with the mean squared, that will just give us negative n times the square of the mean. There. Another thing that we need to know is that, okay, before we can even do anything else, I'm now going to distribute the e, okay, to the inside of the brackets. But I want it to be with the terms that have got a square. So for the first term, we are going to have the summation symbol from the first term to n, and then I'm going to write now the estimator, that is the e. The e, remember, is going to go with the x squared. Okay, so that will be it. And then I'll still distribute the e with the mean squared, but I'll first write the negative n, and then now I'll write the e with the square of the mean. Okay, hope we get how that has come about. So another principle that we need to know is that when you have got the estimator of x squared, this is equal to mu squared plus sigma squared, and when you have got the estimator of the mean squared, this is equal to mu squared plus sigma squared divided by n. So now we're going to substitute on top. That gives us summation from the first term to n. So where there is this guy estimator of, we can see what we're going to substitute. We are going to put mu squared plus sigma squared, and then we have got minus n. Where we've got estimator of the mean squared, what are we going to put? We're going to put mu squared plus sigma squared divided by n. Remember what we said when we said that when you have got the summation from the first term to the next term of any number, it is just getting n, you multiply with that number. So this therefore is going to be n multiplied by mu squared plus sigma squared, and then minus would distribute also here, but I can first write it like that. So let's distribute. This is going to be n mu squared plus n sigma squared minus n mu squared, and then the negative n times sigma squared over n, that will be negative sigma squared. So can you see that this will cancel with this, and what are we going to remain with? Remain with n sigma squared minus mu squared. Remember at the beginning we said that first we'll leave out the denominator. I'll bring back the denominator. So we are having n sigma squared minus sigma squared. I'll bring back the n minus 1 which was in the denominator. On top, I'm going to factorize sigma squared. We'll remain with n minus 1. Down we also have n minus 1. Can you see that this will cancel with this? And that will give us sigma squared. Hence, proven. Okay. Remember how the question was? Prove that the estimate of the sample variance is equal to the population variance. And that is how you go about this one.